Hello class, welcome to my quick primer on working with wiring for electrical prototyping. We're going to start off this video by actually talking about different types of wires. We're going to then do some soldering, and we're going to finish up with some different types of mechanical connections in order to join different electrical components together. To start off simple, we've got a couple different types of wire right here. This is a single conductor wire. It can basically send only one electrical signal. If I strip it, these may look like silver wires, but don't be fooled. They're copper tinned wires, so they're majority copper with a tin coating. You'll notice that this wire is incredibly flexible, and that's for two reasons. The first is that this is a silicone insulation, and the second is that if I strip off more of the insulation, what you'll be able to see that this is actually individual strands of wire all packed together. And so there's space in between those strands, which allows them to slide over each other and provides much more flexibility. This wire is amazing for electrical prototyping, where you're not sure where the wires are actually going to need to run at the end, and you want to have as much flexibility as possible. The only drawback of using stranded wire over solid core wire is that you have less material if you took a cross section of the wire, so it can carry less current. So if we zoom in on this wire, you may be able to see that this is a 20 American gauge wire. If you compared that to a 20 gauge solid core cable, it would have less current capacity. Solid core wires are used to wire houses, and they're pretty much used for really high current carrying applications. We're going to almost exclusively use stranded wire. So in addition to the single conductor cable, we also have this multi-conductor. Inside of this black insulation, which is PVC, it's not as flexible as the silicone wire, and it's not as heat resistant, but it's a little bit cheaper. We have four 24 gauge wires, and each can be stripped to reveal bare copper cables. There's no tinning here. The difference between bare copper and tin copper wire is that the tin protects the copper in oxidative environments. So wet environments, hot environments, you're going to want to use a tinned copper wire. I don't expect for your initial prototypes that the difference between a tinned wire and a bare copper wire is going to be a decision driver. The reason you may want to use a multi-conductor cable is that you want to keep similar signals together, or even pairs of signals. So for example, this motor right here has 4 wires, so it would be nice to use a 4-conductor cable to hook this motor up to some kind of controller. We keep all of the wires together, so not only is it a convenience thing, but it's also an organizational factor for using multi-conductor cables. Perhaps this is pretty obvious, but with multi-conductor cables, the conductors run parallel to each other, and when wires run parallel to each other, there's a high chance of them exchanging noise. So a rule of thumb here is that you want to keep like signals together. So if these are all 5 volts, that's fine. You don't want to have a wire that's high voltage, say 1,000 volts AC, running next to a couple lowly data signals. You're going to have just a mess of noise. I wouldn't necessarily describe this other type of wire as a multi-conductor cable, but this is also a really nice way to keep your wires together. These are commonly used for LEDs. So there's 3 wires here and they're kind of glued together, and you can separate them if you want. The nice part about this setup is that you don't have to strip off an extra layer of insulation, but you still get the added benefit of the wires staying together. Let's talk about how to appropriately strip wires. Now, there are many fancy devices to strip wires, but I like the old-fashioned manual wire strippers. They just work every single time, and it's very clear how to use them. People often don't have these laying around, and if they do, they might have the wrong size. So the tendency is to reach for like a pair of scissors and to just barely grip onto the insulation and pull it off. Now the problem with this method is that you're likely to shear, especially with stranded wire, some of the strands off. Now you've unknowingly changed the diameter and thus the current carrying capacity of this wire, and it could be a fire hazard. So never use scissors to strip wires. You can use them though to cut off the end of a wire, especially one with such a soft insulator like this silicone. The proper way to strip wires is to always use a pair of strippers. Now, if you see here, there's two different size grooves. We've got the yellow strippers. This does lower gauge. Recall that the lower the number for the wire gauge, the larger the wire is. So a 20 gauge wire would be larger than a 24 gauge. So these yellow strippers are used for wires that range from 18 to 10 solid, 20 to 12 stranded. That's right, you use a different pair of holes whether your wires are stranded or if they're solid core. So the yellow strippers are for larger wires, the blue strippers are for smaller wires. So this one goes from 30 to 20 solid and 32 to 22 stranded. So the appropriate way to use the strippers is to determine what the gauge of the wire is by looking at the insulation. But this is 20 AWG. So now we need to find 20 AWG on the stranded. Now these strippers only work for as large as 22, so we need to go to the yellow strippers. Here we can see 20 stranded, put the wire right there. And generally we're looking to take off, I would say anywhere from 1/8 of an inch, about 3 millimeters to 5 millimeters, maybe even 6. And that's it. When we use the appropriate notch in the strippers, we don't take off any of those extra strands, which would affect the diameter of the conductor. The problem with multi-conductor cable is that it's very difficult to get this outer shield off so that you can strip the wires to reveal the conductor. Now typically they make special tools for each different type of multi-conductor cable. So there's a very specific tool for removing the outer insulation of, say, an Ethernet cable. We don't have that luxury, so we have to be incredibly careful on how we remove this insulation. What I like to do is just take the scissor part of the strippers and gently press down on the handles to make a serration around the cable. You can see here that I haven't damaged any wires in this process. It's very easy to accidentally cut one of those conductors during this process, which is not good, and you'd have to start over. So once I make that little cut, I kind of bend the wires back and forth just as much as required to make this little gap grow. And using my fingernails, I can pull the insulation off. Again, try not to dig into the insulation underneath the black insulation. Because these are the problems that are hard to catch in wiring. Say you have some kind of short here because you nicked this insulation, you nicked one next to it, and now the current's jumping from one wire to the other. It's very, very difficult to detect, especially if you have an assembly with hundreds, maybe even thousands of wires. All right, let's talk about soldering now. Say you want to join one wire to another, or maybe you want to splice one wire into two wires so you can supply power to multiple components. The easiest way to connect wires is going to be, in my opinion, soldering. You don't have to search for any type of specialty connectors. All you need is a power supply, an iron, and a little bit of solder. And you can join two similar materials, usually two copper strands. Now this whole setup right here is actually known as a rework station. It has not only a soldering iron, but it also has a way to remove soldering. This is like a fancy vacuum gun, as well as a way to blow hot air for when you're working with solder paste. We have this system available in the digital fabrication lab. So you're not only capable of soldering wires, but you can also kind of tweak circuit boards as well. We're just going to focus on the soldering iron portion of the system, and you'll find soldering irons all over Vanderbilt in different maker spaces. So I'm going to go ahead and turn on the station. We can hear different fans spin up. The temperature reading for the soldering iron right now is 570 degrees Fahrenheit. The lead-free soldering that we're using melts at about 650. I actually have a preset for this. It's the digital system. You may have an analog soldering iron where you actually have to adjust the knob to this temperature. Either works well. The solder comes in different diameters. Now, it's quite obvious that you would want to use a larger diameter wire if you have to solder multiple wires together or solder large diameter wires together. For general purpose soldering, I like to use a 0.8 millimeter or 1 millimeter diameter solder. And basically solder is mostly tin with a little bit of silver. But on the inside of the wire, that's just the outer sheath. There's actually this substance called flux, which cleans the component and helps the solder flow. And there's a limited amount of that flux, and it burns up as you use it. So when you're practicing soldering, try and get that correct joint as quick as possible. And we're going to take a look at that now. Before we do that, I want to talk about two safety things. So first off, iron always needs to go back into its holder, okay? If you place this thing on the desk, you place it near the edge, people are going to run into this. They're going to get burned. The other thing is that even though this is lead-free solder, it does produce some fumes which can be noxious after a while. So right here we have this kind of charcoal and HEPA filter fan. We're going to turn that on as well. There you can hear it running. I'm just going to do a little bit of soldering in this video, so I'm not going to keep it running just for the purpose of being able to commentate over this. Now with soldering, you have to hold the two wires, feed the solder, and hold the iron. You practically need 4 hands. So that's why I have this little assembly right here. It's called the soldering helper. And basically it can hold wires. These are posts for holding PCBs. And you can position everything as you need to, and then come in with the solder and the iron. The last thing to be mindful before soldering is the health of this tip. Now perhaps it's obvious this is called a soldering iron. The material this tip is made out of is iron plated copper, and basically this heats up to a really high temperature and it melts the solder. Now the problem with it being iron is that iron is prone to rusting, oxidation, and so what you do after you're done soldering is you leave a little bit of solder on the tip to protect it from oxidizing. Because once it oxidizes, there's a lot of problems. Oxides or insulators, you have problems melting the solder, you have problems getting the solder to actually stick to the tip, okay? So once that happens, pretty much the tips are done. You can use flux sometimes to clean them off, but generally when we're done soldering, we want to leave a healthy amount of solder on the tip. But then when you turn the soldering iron on, we need to clean off all that old solder because there's no more flux left. And that flux is what really gives the solder that nice property of being able to join metal. So to clean off the old solder that was used to preserve the tip, we swirl it around the iron in this kind of brass mesh. And now you'll see we've got a very nice shiny tip. Again, there's just so many details, I don't want to go into all of them, but the size of your tip is also going to affect if you're able to solder really delicate components or really large ones, okay? In the lab, we've got different tips, and feel free to consult me on determining what size tip you should use in order to get the kind of quality that you want. I want to move the camera and set up some wires in the solder helper. Again, I'm going to put the soldering iron in the holder while I set everything up. The problem with the flexible wires is it's harder to position them and make them stay put. There's a lot of different opinions on the best way to position two wires and solder them together. Do you put them parallel side by side like this? Do you put them on one side and you twist them together? NASA actually has their own standard for soldering, which I'm definitely not adhering to right now. But in my book, soldering joints should never experience any kind of mechanical force. So as long as you can get the wires close together, cover them with a healthy amount of solder, not too much, we'll talk about that in a second, you're going to be good to go. We can collect all of these strands, just make sure they're nice and tight. We don't want them sticking out everywhere after we're done soldering. This 20 gauge wire is pretty thick, so this 0.8 millimeter solder that I'm using now is not ideal. I'm going to have to feed quite a bit of it to cover up the joint, but we'll make do. So solder flows to hot components. So the first thing I do is I like to warm up the wires. Now you don't want to warm up the wires too much if you've got a low temperature insulation like PVC, but these are silicon coated wires which can go up to 200 C. So once I give them just a little bit of warmth, I can go ahead and start melting the solder. Now I'm not in the ideal orientation at all because I'm filming, but I'm getting a nice coating. And what we're going for is not like a huge bubble, but we just want to make sure that the joint goes all the way around the two wires, and that we don't have a lot of those strands kind of sticking every which way, because those could be shorts down the line. Now that we have a nice solder joint, we need to protect it, because this is an exposed electrical connection that could short our circuit or even possibly electrocute a user. So we need to coat this in a non-conductive material, and we're going to use something called heat shrink, which is made out of a polyolefin or even PVC. I know the zoom is a little bit close, but I have this kit with several different sizes of heat shrink. I'm looking for the closest diameter heat shrink to the solder joint. This right here looks like it'll work. And basically we're gonna want, probably a 1/4 inch, maybe even 3/8 of an inch on either side of the solder joint to make sure it's nice and protected. And basically what you do is you slide the heat shrink on one side, go over the joint, nice. And then we use a lighter to just heat up the heat shrink. We don't actually want to touch the flame to the material because it'll actually burn. But here you can see under the heat, it's conforming to the shape of the wires and the solder joint. Now be careful because that's hot. I'm just going to flip this wire over just so I can heat the other side as well. Fantastic. Just as a real quick example here, let's say I wanted to go from 2 wires to 1 wire. Well, I strip off a little bit of extra material so that I can twist these 2 wires together. When you twist them together, you lose a little bit of length. Okay, put this in my little alligator clips. In addition to soldering wires, we can also solder what is known as through-hole components, such as this header, which sticks through these conductive holes on a circuit board. This guy actually goes upside down. This is a 3D printer motherboard circuit board. And these little posts right here will fit in these holes and help you stabilize what you're soldering. Now the problem is that the side you solder is not the right way up. It's actually upside down. So there's a tendency for this thing to fall out, right? So we'll use one little hand to hold this component up. Perhaps this is obvious to you, but conductive materials don't only conduct electricity, but they're also really good at conducting heat. So when soldering, one, don't ever have your friend hold the wire because it's going to get hot. And the other thing is that we need heat to melt the solder. So if I were to rest this board on this metal plate, the heat that I'm trying to use to melt the solder on these pins and secure them to these holes will be transmitted to this plate and dissipated, so I won't be able to solder very well. Everything here is non-conductive. So yes, this looks like it's just a small surface area of brass, but this goes down to a plastic bit down here. Let me zoom you in before I start soldering. When you're at a soldering station, it's not uncommon to see a tool like this. It's a flux pen, and people love to douse their electrical components in the liquid that comes out of this pen. But this is not needed when you're using flux core wire. In fact, it can just make the whole process really messy. So avoid using these flux pens unless you're soldering and resoldering the same joint a bunch of times. The soldering tip I actually have on here is too big for this, but I would have to wait for this thing to cool down before I could solder. So this is one example of when you'd want to switch tips. We're just going to roll with this for now. But basically, I'm going to heat up both the pin of the header as well as that circular bit around the header. Remember, solder flows to hot components. And that's it. What we're looking for is just a little bit of solder, especially here if you put too much, it's going to join other electrical connections that you don't want to be joined together. We're looking for a slight concave shape to this cone because that means there's some surface tension. It's sticking to the pin as well as this silver bit around, which is making the connection to the board. I will do one more. So here's a great example of a bad soldering joint. We don't see that concave geometry. So what I need to do is heat up both the pad and the pin again, and hopefully we can get the correct kind of joint. And that is something I'm a little bit happier with. Again, I'd be able to do much cleaner work with a smaller tip. And that's the quick introduction to soldering. Soldering is really an art form, and it takes practice to get good at it and to identify what are good solder joints and what are not. But let's quickly go over a cleanup. So before we turn off the soldering iron, we melt just a little bit more solder on the tip. Just a little bit, that's perfect. Put it in the holder. Again, I need to emphasize this. Please always put the soldering iron in its holder. That's why it's here. Placing this on a flammable surface or someplace where someone could touch it is really bad. After that, we always turn off the power supply to make sure the irons don't stay hot. While soldering is very useful and great in a pinch, very few electrical connections outside of a circuit board are actually soldered together. If you think of like an automotive wiring harness, all of those connections are mechanical. And so let's go ahead and start talking about mechanical connections, and we'll talk about why those are superior in commercial applications. To start off this mechanical talk, we need to wire our regulated DC power supply. So this box right here converts AC power into DC power, and this is an AC cord. So somehow we need to get AC power to this regulated power supply. I'm going to cut off the end of this cable with my wire snips. I'm going to be careful, very careful, especially for 110 volt AC power, to remove this insulation for this multi-conductor cable. Just to emphasize, there's 3 prongs on this cable, so there's 3 wires in here. Live, neutral, and ground. I got a nice clean break there without cutting into any of the other insulators. This white powder, it's actually, I think it's talc. It helps slip the wires in to this black insulation, so don't worry about that. It's harmless. White, black, green, neutral, live, ground. These 2 are required for power to complete a circuit. This one's required for your safety. Now these don't have a wire gauge size on them, but they're most likely 12 or 14. So I'll start off with 12. Nope, 14 it is. One quick way you can kind of determine the approximate diameter of the wire is if you're not able to strip it at a larger wire size, then it's most likely not that size. This is bare copper wire. And so basically, if we look at this power supply, we see ground, neutral, live. And these are what are known as screw terminals. So basically with a screwdriver, you can increase or decrease this space, allowing these terminals to clamp down the wires. And your first inclination may be to just say, hey, this is easy, let's stick the black wire, which is live, into there. Ta-da! We have wired the live wire. Now the problem with this, there's actually quite a few. And 9 times out of 10, these problems will not affect the functionality of this power supply. But we've talked about how dangerous electricity can be, so why take the risk? First off, let me fix the zoom on this. First off, this terminal is not clamped down evenly. Because the wire is on one side, you can see it's on the right side, the terminal is like this. So you're not getting a nice even clamping pressure. The other thing is that these wires are stranded wires. And so if you're not paying attention and you stick one of these wires, as the ground, so that's important, but you stick the live wire and you have one single strand sticking out and it makes contact, if the neutral wire strand makes contact with the live terminal, you're going to be in for a shocking day, okay? So we need to protect these wires, especially when they're stranded, and just with these screw terminals, we want a nice even clamping pressure. So what we can do is use a mechanical terminal to consolidate those wires and allow for the screw terminal to apply a nice even force. So there's many different types of connectors that can be added to a wire. For power supplies, we want to use what is known as a spade connector. Here are the two prongs of the spade connector, and it'll fit on either side of that screw terminal. We can see we've got different colors, red, blue, yellow. This color system is for different wire gauge sizes, with red being the smallest, blue being a little bit larger, and yellow being the largest. And usually these have like an insert to them that tells you what wire gauges are for which color. But if it fits, you're good to go. For this 14 gauge wire, it seems like the red terminal is a little bit too small. So we're going to try blue. The blue connector fits better. So what we can see here is that the wire, the copper wire, is peeking out just a little bit out of this sheathing, which is fine. The insulation goes up to or a little bit before the blue connector, so that we've got no conductive surfaces sticking out over here. We're going to use what's known as a crimp tool, and this has jaws which clamp down on the conductor. We want to be on the front of it. And now give it a little bit of a tug, and we've got a nice mechanical connection. A closer look at the spade connector reveals that there's no conductive material at this first hump of the blue part. You can see how this has a larger diameter, and then a little bit in it, the diameter gets smaller, and you've got that silver conductive piece, okay? So the way to make a perfect connection is to actually have the insulation go up to this ridge and stick the wire through the conductive part. This tool then grips down and mashes that conductive part into the wire. Okay, you can see how that diameter got smaller. And now you're going to have metal on metal, and this spade is then going to be conductive with whatever signal or power is coming from the wire it's crimped on. So I went ahead and added the spade terminals to both the live, neutral, and ground. I can then go ahead and connect them to the power supply. And there we have a nice, safe, and very strong connection. The reason we wire this DC power supply is to supply power to this Duet 3D printer motherboard. And this is the exact board that controls the movement of all of the Voron printers in the digital fabrication lab. This board needs 24 volts power, and we're in luck because this power supply supplies 24 volts DC. Now, we've got a problem here because the input terminal for the positive and the negative power comes through this component right here. This component right here is known as a screw terminal. And basically the way it works is it has this gate where you can stick a wire in, and then when you turn this screw that's on the top, that gate closes. And when it closes, it clamps down on that wire, okay? But here on the DC power supply, we can see that we've got 3 screw connectors for positive 24 volts and 3 screw terminals for negative 24 volts. We just need 1 positive and 1 negative. Fortunately, I have this very slick dual color spool for wiring positive and negative DC voltage. We can see here that this wire is marked to be 18 gauge, which is perfectly sufficient for the amount of current that this board is going to draw. So I'm going to pull some wire off the spool, cut it to the right size. We already know that we need a spade connector on the power supply side. These are 18 gauge, so they're going to use the red connector. They're slightly smaller than the wire that we use to supply the AC voltage to the power supply. I didn't point this out before, but you can see the actual colors on the crimp. So this is where we put the red connector versus the blue. Crimp it down, nice strong connection, black wire. Time for the red wire. Typically the color nomenclature is that red wire goes to positive and black wire goes to negative. First 3 are positive, next 3 are negative. Now once again, the inclination may be to just stick these wires right into the screw terminal, okay? And again, 9 times out of 10, that would work just fine, but 10% of the time, let me show you what will happen. This is being dramatic, but your stranded wires will make connection with the next door terminal, okay? And now we've just fried a $100 board. Not good. So once again, we need to collect the strands of these wires, and clearly a spade connector is not going to work for this application. So we're going to use what is known as a ferrule. And basically, this is a straight connector. And here I've actually not lost the little insert. So we've got an 18 gauge wire. So for 18 gauge, we need the red connector. And what we can do here is we go from basically a stranded core wire, which has all the benefits of it being flexible, to a solid core connection. So I can slip over this connector, which is known as the ferrule. This red part should cover the insulation, while the actual conductive tin part of the copper wire should go into the silver part. I might give it a twist just to consolidate those wires. Okay. Now before, with the spade connectors, we crimped the entire thing, but for this we just crimped the silver portion. And so we have, once again, a different tool. And basically, you can see how it closes those jaws. And it's going to compress the conductive part onto the conductor of the wire. And there we have a nice solid connection that we can tug on, make sure it's nice and secure. We'll repeat the same process with the black wire. The ferrules are super easy to crimp on. And if we can see here on the bottom of the board, we can see that positive is going to go on the right and negative is going to go, or ground is going to go on the left. So ground on the left, positive or 24 volts on the right. And now I'm sure that we've got a great connection between the power supply and ultimately our printer controller board. I'm starting to reveal why the mechanical connection is superior to the soldering joint. It's basically removable. So when we talk about automotive or any other type of industry where it's common to repair expensive components, we don't want to have to desolder something. That's very unpractical. But to be able to unhook, unscrew an electrical connection, test a sensor, possibly replace it, is one of the only things keeping your car repair bill below a manageable level. The last type of mechanical connection that I want to talk about is known as a JST connector. JST stands for Japan Solderless Technology. It's basically an umbrella term for all quick disconnects when it comes to connecting to pins that look like this. These pins over here are for stepper motors, just like this one right here. 4 wires coming out of the stepper motor, 4 pins coming out of each connection. Now let's pretend like this 4-conductor cable from earlier on in the video is connected to this motor. We need a way to connect to these pins. Here is a JST connector. And the most notable features about this connector is that it has 2 wings. This top wing right here is for grabbing onto the insulation. This bottom wing is for connecting to the actual conductor. And this piece right here is what's going to make contact with the pin. It's like a little spring that's going to apply constant pressure to that pin that's located on the board. A common theme with all of these different connectors is that they all require a different crimping tool. So this is one that's great for JSTs, but because JST is such a generic term, you could require, a couple different versions of this tool right here. The Digital Fabrication Lab has all the different crimping tools that you could possibly need. So if you have an electrical problem, we could probably help you figure it out. But let's zoom in on this crimping tool. In here we have 3 sets of jaws. If I actuate the tool, these bite down and once again are going to apply a pressure. But in this case, instead of like mashing down the connector onto the wire, it's a little bit more eloquent than that. So let me just show you here by inserting this JST connector into the end. So watch what happens to the connector. The grooves actually cause this to kind of wrap inward. It's going to hug the wire. So let's do that again with an actual wire. We'll take the crimping tool, we'll set the connector in that. And this is a ratcheting tool, so it's got different levels that it'll stay at. Something that's very important is that we don't crush this tab on the back here, because this is actually what's going to retain this connector in the housing. And that'll make more sense in a second, but don't crush that tab, okay? We're going to go ahead and put one of the wires in there. And now this is a little bit of a judgment call. We want the wire to go into that second wing. And so I've done this quite a few times. I'm familiar with how far to stick it in there, but this is going to come from practice. I went a little bit far, but here we can see that this top one is on the insulation, and this second wing, it looks like it's biting on the insulation, but I double checked and it's not. It's biting on the wire. But let me do the second one and just not insert that wire as far to make sure that we've got a nice electrical connection. Stick the wire in. I'll be careful not to go in as far this time. And here is a perfect example. So here you can clearly see we're just biting on the insulation for the first wings. The second one are touching the wires. And here you can see how this electrical connection is happening mechanically. I'm going to do this 2 more times. And now I have all 4 JST connectors crimped on. Very nice. We're going to talk about this more in a future class, but basically the order of these wires is going to matter for wiring a stepper motor. And what's really cool about this connector is it actually has these ridges, which will only allow you to insert it one way on the board. We'll talk about that more in a second. So we didn't break those tabs, and so those tabs are actually go on the back of the connector. So watch when I insert this. It snaps in there. That tab grabs that top face, and now the wire won't come out. So if you want to pull this wire out, you have to bend that back down. Again, we'll talk about this later, but the order is red, blue, green, yellow. Now we're going to practice, obviously, how to make these connections in class, but the best part about this connection is that I can plug it in. Again, it's polar, so it remembers this order. Plug it in, remove it. Plug it in, remove it. So that was actually a pretty thorough look at wiring, soldering, and mechanical connections. This video should serve as a great guide as you work on wiring with projects in this class and out of this class. And with that, I'll catch you guys in class.